The sheer scale of the universe is a terrifying reality. Even if we use our most powerful telescopes to spot a perfectly habitable, Earth-like planet out there in the cosmos, we are currently trapped inside the Milky Way galaxy. For any individual human, leaving this galaxy is a physical impossibility. Take our nearest neighbor, the Andromeda Galaxy. It sits approximately 2.5 million light-years away from Earth. This timeline chart compares exactly what that distance means for us. If we launched a standard spacecraft today, cruising at 28,000 kilometers per hour, the journey would take 94.5 billion years. Even if we somehow engineered a ship capable of traveling at the absolute speed limit of the universe, the speed of light, the crew would still spend 2.5 million years in transit. Linear travel is a dead end. If humanity is ever going to spread across the universe, we have to find a way to manipulate the geometry of space-time itself, effectively bypassing the physical distance between galaxies. In 1915, Albert Einstein submitted a paper to the Prussian Academy of Sciences in Berlin. It proposed a radical new architecture for the universe. This proposal took occasional form of 10 highly complex, nonlinear partial differential equations. Today, we call them the Einstein field equations. These equations dictate how matter and energy influence the curvature of spacetime. Imagine a stretched mesh grid that sags under the weight of a heavy object. Heavy planets and massive stars warp the fabric of the universe exactly the same way. The math involved is so dense that Einstein himself could only produce approximate solutions for specific cases. He had provided the rules, but he hadn't identified every possible outcome they allowed. For over a century, physicists have interrogated these equations, hunting for exact solutions that might predict physical anomalies. They are looking for mathematical loopholes, phenomena that could solve our distance problem. The first major breakthrough happened just a year later, in 1916. A physicist named Carl Schwarzschild managed to solve the exact curvature for a single heavy mass. His math predicted what happens if a star collapses into a point of infinite density. The mass curves the space-time mesh so violently and wraps it so tightly that the region entirely pinches off from the rest of the universe. Schwarzschild had mathematically discovered the black hole. Then, in 1935, Einstein and his assistant Nathan Rosen identified another specific solution within the equations. They discovered a bridge connecting two distinct points in spacetime, a structure we now call a wormhole. Think of the universe as a flat sheet of paper. Traveling from point A to point B on the surface takes a long time, but if you fold that 2D space through a higher dimension, a wormhole creates an instant tunnel. Applied to our escape plan, point A is the Milky Way and point B is Andromeda. This wormhole bypasses the 2.5 million light-years entirely. There is a massive engineering flaw here. To rip open a tunnel in spacetime, you need intense, crushing gravitational force. A black hole has that kind of power, but its gravity is inescapable. Anything that enters is trapped forever. It acts as a dead end, not a door. An escape tunnel is completely useless if the entrance crushes you into atomic dust. To make this highway function, you need an exit point that repels matter, not traps it. In 1964, Russian theoretical physicist Igor Novikov identified a solution that functioned as the mathematical time reversal of a black hole, the white hole. A white hole does the exact opposite of its dark twin. No light or matter can enter its event horizon. It acts as a boundary of no admission that violently spits out energy and matter into the universe, making it a blindingly bright anomaly. This creates a theoretical architectural pair. To leave the Milky Way, we would need a black hole to drag us out of normal space, funneling us through a wormhole, and a white hole to safely eject us into a brand new galaxy. White holes are highly controversial in physics because they appear to reverse the flow of entropy. The second law of thermodynamics dictates that things break down over time. A shredded piece of paper cannot naturally reassemble itself. A white hole doing exactly that seems impossible. Yet on June 14, 2006, the Swift Space Observatory captured a massive, inexplicable flash of white light, known as GRB 060614. Normally, a flash like this happens when a black hole swallows a dying star, but there was no star. It was an empty void, leading some scientists to hypothesize they had just witnessed a physical white hole. We have to remember that mathematical predictions have a habit of becoming physical reality. For 100 years, black holes were nothing more than numbers on a chalkboard, until 2019, when we finally photographed one. The math for wormholes is stepping off the chalkboard too. In 2015, researchers in a laboratory successfully engineered a synthetic magnetic wormhole using high-temperature superconductors. Every magnet naturally has a north and south pole attached to each other. This device successfully separated those poles across an invisible gap, bending a magnetic field through a hidden tunnel, exactly the way a cosmic wormhole bends space-time. The solutions predicted by Einstein's equations are slowly materializing in the real world. The theoretical foundation to leave the Milky Way was established over a century ago. The only test left is whether humanity can survive long enough to build the ships.